All right, so we're going to continue this idea of looking at functions and their graphs. And let's take another look at sort of how they change, right? We've looked at increasing, we've looked at decreasing, um, and we want to take sort of one more look at the way that they're changing over an interval. We'll start actually by taking a look at a graph of a car traveling on, say, a road trip, right? Just like back in the before times where that was possible and safe and all that. So let's say that this, car trip, they record the hours that they've traveled or driven, say 1, 2, 3, 4, and the miles that they drove in that time, right? Let's say this is 100 miles and this is 200 miles. And there's some graph that explains this, right? Say at hour 1, they were at 50 miles, hour 4, they were at 200 miles, and between that, maybe they did a little something like this, right? And they sort of got to their destination right at the 4-hour mark. One of the things that we might do with this in, say, a physics class, right, is calculate the average speed that they were moving over that time, right? Say if you're looking for the average speed between hours 1 and 4, right? So the average speed, and we'll kind of say hour 1 to 4, right? And the way that we always did this in our physics classes, right, is we would take the distance divided by the time, right? So the distance traveled between hours 1 and 4, I guess we'll write as the distance over the time, right? So the distance would be 200 miles minus 50 miles, right? Because that's where we were at hour 4, that's where we were at hour 1, divided by the time it took, right? Which is going to be 4 hours minus 1 hour, which looks to me like 150 over 3, or 50 miles per hour, right? That's the average speed that they were moving over time. But let's see if we can write this in function notation, right? Let's call this, I don't know, s of t, right? S, just being one of the generic function value or function names that's used on this a lot, right? Well, that would mean, sort of looking at this idea, that our average speed can actually be written as s of 4 minus s of 1 over 4 minus 1. And what I want you to notice, right, really, really quickly, is that this is the equation for the slope of a line, right? It's the function value at one point divided by, or minus the function value at another, divided by the difference between those two inputs. Well, what line is this the slope of? Well, it would be the slope of the line that passes through the 2 points we're interested in, right? It would be the slope of this line right here. And that tells us that the slope of this line tells us the average speed of the car, okay? So the average slope of that line, the speed, right, over that time is the average change in the graph, right? So we can absolutely do this on an arbitrary graph, right? Once again, let's grab a set of axes. Let's grab some random function, right? Some sort of squiggle. We'll say our squiggle looks like that right now. And we're looking for a sort of analog, right? Some average amount that it changes. So let's pick 2 points on it, right? Let's say this is A, and we'll say that this is B. And if you remember, right, our specific case up here, we took the slope of this line, right, which was the total change divided by the input change. right? And I suppose I'll draw that little triangle for us. The total change, which is here, right? This is how much the function value changes, divided by the inputs required to change it that much, right? And we can create a direct analog of that on here, right? We could have, say, this is representing, this is b minus a, right? This is the length, this is how much our function input is changing over this period of time. And this is how much our function output is changing over this period of time, right? This is f of b minus f of a, right? What some people would call the net change. And if we connect these 2 points with a line, say like that, the slope of this line is the net change divided by the change in input, or the average amount that we're changing, right? This sort of gives us an idea of it's approximately trending up, or it's approximately trending up a lot versus a little, right? And we call this the average rate of change. It's usually abbreviated ARC, right? And that's we'll say it's of f on a to b, right? And that is equal to the slope of this line, right? Which is f of b minus f of a divided by b minus a, right? This formula here, we will use it a lot. I'm going to do some examples for you with it, but it will keep coming up, and as with many things this section, it will come up again in calculus in a really cool and really big way. Okay, so let's do some examples to kind of leave this abstract weird land. Right, so let's say f of x is x minus 3 squared. Let's say find the average rate of change of f, say on the following intervals. We'll say a, x equals 1 to x equals 3, and b, x equals 4 to x equals 7. I'm actually not going to graph this. We're just going to go through the algebra on this guy, which is totally fine, right? Because a lot of the themes right now are connecting our algebraic expressions to our graphical expression. So let's start with part A, right? Our average rate of change is going to be average rate of change of f on 1 to 3. Well, that's going to be f of 3 minus f of 1 over 3 minus 1, right? Well, what's f of 3? Well, that's 3 minus 3 squared minus 1 minus 3 squared over 3 minus 1, which is 2. But this guy equals 0, and so it looks like we're going to be minus negative 2 squared is 4, so it's minus 4 over 2, or negative 2, right? So on average, right, we're decreasing at sort of like 2 units per unit, you can sort of think, right? Like we're on average decreasing with a slope of negative 2. Okay, well, what about B, right? What's the average rate of change of f on 4 to 7? Well, that's f of 7 minus f of 4 all over 7 minus 4. That would look to me like it's going to be 7 minus 3 squared minus 4 minus 3 squared over 3. 7 minus 3 is 4. 4 squared is 16. 4 minus 3 is 1. 1 squared is 1. So that looks like 15 over 3 or positive 5, right? So the average rate of change of this graph on 4 to 7 is positive 5, right? So we're getting bigger fairly substantially as compared to how we were getting smaller here. Okay, let's do one more example. So if you drop a rock, right, off of some tall building, you kind of go up there and you drop off a rock. It's going to fall at a rate of this. Say my distance as a function of time is going to be 16 t squared, right? That's how fast it's going to fall as a rate of time. So let's find the average rate of change of d of t on, we'll start with part A, t equals 1 to t equals 5. Well, as we've seen, my average rate of change, and I'm not going to fill out the information because it's just right here, right? So, you know, it should say here of t on blah, 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 but we have that right here. That's going to be t of 5, or d of 5, minus d of 1, all over 5 minus 1. All right, well, d of 5 is going to be 16 times 5 squared, minus d of 1 is going to be 16 times 1 squared. It's going to be all over 4. And we could totally, you know, try this big multiplication, but I'm actually going to notice that I can factor out 16 times 5 squared minus 1 over 4. But that's actually just equal to 4, because 16 over 4 is 4, times 24, right? Because 5 squared is 25, minus 1 is 24. And 4 times 24 is 96, right? So our average rate of change from t equals 1 to t equals 5 is actually fairly substantial. We're speeding up quite a lot. This would be in units, feet per second, right? Because this is actually the calculation of the average speed, right? Because we have a function that models distance. We'll do part B now, right? Let's say we're going between t equals a, so we'll go 2, t equals a plus h. To sort of help you get a better idea of what this is asking, I'll kind of do a little sketch of this graph in the corner. So we have our axes. So we have our graph. It's going to look something like this. Right? It's half of a parabola, right? Because we can't have negative time. So what this is asking, right, is if you pick some point A, and I take some step to a plus h, right? That's, you know, maybe all the way up here. We can draw our sort of slope like this. And so this is asking, like, given some point A and some step length h, what's going to be the slope of this line? And it may seem very algebra intensive, and it is to a degree. But if we trust our algebra skills, it should be fairly straightforward. So the average rate of change on D, or of D, on A to A plus H, well, following our thing, that's going to be D of A plus H minus D of A over A plus H minus A. Okay, well, D of A plus H is going to be 16 times A plus H squared minus 16 times A all over H. Let's factor out that 16 to make our lives a little bit easier. Times A plus H squared minus A squared all over H. Squaring this term here, right, we're going to get, that's a binomial, so it's going to be a squared plus 2ah plus h squared. We're subtracting a squared and dividing the whole thing by h. Well, we have some things that cancel, right? This a squared cancels with that a squared. So it would look to me like we're left with 16 times h squared plus 2ah. But since we're dividing by h, I can actually factor out an h out of both of these terms, right, to get 16h times h plus 2a divided by h. Now, these cancel, right? And it looks like we're going to get 16 times h plus 32 times a, or you can keep this factored, right? So if we're looking for our rate of change, our average rate of change, on any interval from a to a plus h, well, now we have our thing, right? You might notice this difference quotient here, we actually did something like that earlier in the quarter, and that's because, as a lot in this section seems to point to, it will come back in a big way in calculus, and it's handy to have an idea of how to handle them right now. One quick sort of aside, what happens when we look at the average rate of change on a decreasing interval or an increasing interval, right? So say we have a function. Let's get ourselves two nice little squiggles here. Say we have a function like that, and we have a second pair of x's here. Let's say we have one that's decreasing, and we have one that's increasing. Well, what happens when we find the average rate of change on any interval where we're decreasing? Well, anywhere we're decreasing, right? If we pick 2 points, any 2 points, we're always going to get a negative slope, right? So let's kind of write that down here, right? We have decreasing equals negative slope. We'll say negative average rate of change, okay? So what about increasing, right? If we're increasing, well, just from the picture, right, we should always get a positive average rate of change. And I want to ask you sort of why that is, right? Why is it the case with that? Well, we said that on an increasing function, any step I make to the right, I have to be stepping up. Well, let's make this step to the right the same that we're stepping to find the average rate of change. Well, then we must be stepping up, so we're going to get a positive slope. Similarly, for decreasing, we said that if we take a step to the right on a decreasing function, we need to take a step down to get back on the function. Okay, well, that's almost directly what it means for our average rate of change to be negative, right? So if we have an increasing function, we have a positive average rate of change, okay? What about the other way, right? Given a function with a negative average rate of change, does that mean it's decreasing? Or what about a function with a positive average rate of change? Does that mean it's increasing? And unfortunately, not quite, right? Let's say, we have some function like this that kind of squiggles, right? If I were to do this, well, that has a negative average rate of change, but it is not decreasing on that whole interval, right? This little squiggle comes up and we're increasing here. So what I want you to think about, sort of in your own time, think about if there's a way that we can amend this idea of an average rate of change. Is there anything that we could do to sort of guarantee that it goes the other way? Can we change this definition at all, add something, take it away to make that true? That's a question that you will answer, again, in totality in calculus, but it's sort of fun to be thinking about now. So we have this idea of average rate of change. How else can we use it, right? We saw that in drawing the secant line through the graph, right? That's what these guys are called, right? These are secant lines. It touches at 2 points. When we're drawing these secant lines through the graph, we get the average rate of change. But what if our function is a linear one, right? One that looks like ax plus b. What happens then? So let's give ourselves a function, some linear function, right? And remember, linear functions look like lines. Well, if we find the average rate of change of this, we're going to draw a secant line through it, but that's just going to be the line itself, right? So the average rate of change of a line is just the slope of the line, okay? And this is actually tremendously powerful, right? When it comes to modeling real-world situations, often the first thing that we'll do is assume that they're linear, right? And if we have more complicated models, we'll get into those later in the quarter. But often most models in the real world start as linear ones, okay? So let's give ourselves a little model to kind of play with and see how this rate of change and these linear models can work together. So let's say we have some tank, right? I am not an artist, but I can still try a little bit. I don't know why that one didn't snap. Let's call that, look at that, great tank, okay? And let's say right now it has 5 gallons of water in it, okay? Let's say it has a capacity, of 18 gallons. And normally when you are given a problem like this, you'd give it as a big word problem. I'm going to be telling you the word problem while I draw the picture because, I don't know, writing down the whole problem doesn't seem like a good use of my time or yours. This is very similar to some of the problems in section 2.5, if you want to get some more practice with that. But we'll also have problems like this on the homework. Let's say we have a capacity of 18 gallons, and then let's say we're filling it. Let's say we're filling it at a rate of 1 gallon every 2 minutes. Okay. So the first question, right, is how long before it's filled up? Okay. And then we'll say, after it's filled, there's a sort of a spigot coming out of it, which is closed right now, but when it opens, water will drain out at say 2 gallons per minute. Okay, and that's not opened until the tank is full. So then how long before the tank is empty? And then we'll say we'll want to create a function to model the amount of water in the tank. Okay. So we'll do this algebraically, and then we'll get a graph of the situation after, okay? So let's just start with part A, okay? I guess we'll label these A, B, C. Well, we know that there's 5 gallons in it initially, and we know that it fills at a rate of 1 gallon every 2 minutes, right? And that would mean that the slope is 1 gallon every 2 minutes times, say, our variable x, okay? So this is a model of how much is in it at any given moment, right? We have our initial plus our changing term. And we want to solve for when we have 18 gallons in the tank. Well, now this is a simple algebra problem, right? If we subtract 5 from both sides, we're going to get 1/2 x is equal to, it would look to me like 13. So that would mean that x is 26. Okay, so we reach capacity at 26 minutes. So we'll write that down. Make sure to spell it right. Okay, now part B, right? How long before the tank is empty? Well, let's just sort of use some logical skills here. Okay, so if at 26 minutes there's 18 gallons, if it empties at 2 gallons per minute, and there's 18 gallons, it should take 9 minutes, right? It should take 9 minutes to empty, but we're already at 26 minutes. And that would tell me that it would be all the way empty at 26 plus 9 minutes, or 35 minutes, right? And I guess I'll label these empty and full. Okay. So here's the question, right? With this information, can we build a function to model this, right? And it would almost certainly have to be piecewise, right? So let's do part C. Let's name it T, right, for total amount of gallons. I guess you could name it V if you wanted. That's going to be at X. It's a piecewise function, right? As we saw, it's going to fill at a rate of this, right? 5 plus 1/2 X. So the first part of our piecewise function is the speed at which it's filling plus the initial amount from time 0 to what? Well, it's going to be filled until we have 26 minutes in order for it to be full. So 0 is less than x is less than 26. And then here's the hard part, right? We have minus 2x plus something, right? Because we know it's going to empty at a rate of 2 gallons per minute. So the average rate of change is 2 gallons per minute, or the slope is 2 gallons per minute. So minus 2x plus something, and that's going to go from 26, and as we saw, it's going to finish at 35 minutes. Now the question is, what should go here? Well, we can look at that by graphing our setup. We know it's going to start at 5 gallons, fill pretty slowly, and then empty out pretty quickly. Okay, let's sort of label some interesting points. Here we have 5 gallons there. We know that it's going to be filled at, say, t equals 26 or x equals 26, and it's going to be emptied at 35, and we know the full capacity is going to happen right here at 26, 18. So we're looking for the equation of this line. It's going to be minus 2x plus something. And I want you to do this at home. You know, consider this a homework problem, right? Due on the homework that's due next Monday, the 25th, right? Figure out the equation of this line. You know it's got to pass through this point and this point. You even have its slope. And, you know, as sort of the last problem on your homework, include the full function and a graph of the function. But with that, with this example, we are actually done for the day. So I will see you on Thursday.